called Bitcoin and cd into it. Then I'm going to make a empty package.json file, and I'm going to install one library called Bitcore Explorers. Now, even though Bitcore Explorers is just one single library, it does require a bunch of other libraries underneath it, and all of these libraries combined have all the functionality you could possibly need to interact with the Bitcoin blockchain. That's why I like this library so much. It requires every dependency you would need. The most important one is this one here called Bitcore lib. Now you might be wondering what Bitcore is in the first place. Well, Bitcore is an open source series of software libraries, APIs, and SaaS services for developing on top of Bitcoin, and it's run by this Bitcoin company called BitPay. And all the libraries are maintained underneath the BitPay GitHub repository. Now I'm going to open a node console, and I'm going to load two variables. I'm going to make a variable called Bitcore, which requires the Bitcore lib component of the library, and this is just going to have all the low-level tools for formatting Bitcoin data. I'm also going to make a variable called Xflow, which is going to require Bitcore Explorers. And this is going to contain all the API integrations for interacting with a remote Bitcoin node that BitPay is hosting. And then I'm going to make one more variable called shell, which is just an empty object that I can use as a global variable to write data to, and will make the screencast go a little bit smoother. Now the first thing that I'm going to need to do is to create a Bitcoin address. And I'm going to do that by making a Brain wallet. So Bitcoin private keys are 32-byte hex strings, and almost any 32-byte hex string will work as a Bitcoin private key. So a good way to generate these on the fly is to use a hashing algorithm like SHA-256 that takes arbitrarily linked strings and converts them into 32-byte hex strings. So I can make any string that I want. I'm just going to make one now that's always decoding, bang, Bitcoin, screencast, 1. And then I'm going to multiply that by 1,000. So I have this really, really big slug. And then if I take the SHA-256 hash of this, that can be used as a private key for a Bitcoin account. So the way that let me first save this as a variable called password, and then I can generate the SHA-256 hash by doing bitcore.crypto.hash.sha256, and I need to pass in a byte buffer instead of a string into this hashing algorithm, so I can do new buffer password. And don't worry, because all of this will be on GitHub. I'll make a gist with all these commands. But anyway, what gets returned from this is the SHA-256 hash of that large string that I made, and it's in a byte buffer format. Now, Bitcore does have an object format for private keys, so that's nicer to work with than this byte buffer. So I'm going to convert the byte buffer into the private key format. But first I need to convert it into a big number. So I'm going to do bitcore.crypto.bn.fromBuffer, and I'll pass in that thing that just got back, and then this is that same hash in big number format. And then I'll make a variable which is called var pkey, which is my private key, and that will be equal to bitcore.private key, and I will pass in that big number object. And I should have now a private key that is the SHA hash of that large string that I made. Now, if I want to see the address associated with that private key, I can do pkey.toAddress. And this one FWX thing that's returned here, that actually is my Bitcoin address that is controlled by this private key. Now, one thing to note, this Bitcoin address is not actually the public key associated with the private key in the ECDSA cryptography. There's actually additional manipulation that goes into it to get it into a Bitcoin address. For example, it converts it into something called base 58, which is a format that removes zeros and capital O's, and it removes lowercase l's and capital I's, so that it's a lot easier to look at without getting confused as what the digits are. The full algorithm for converting a Bitcoin address from the key pair to the resulting address is here on the Bitcoin wiki, which I'll link to. But anyway, we have this address now, and if I wanted to, for example, copy this and go to a Bitcoin Explorer like BlockCypher, live.blockcipher.com, and type in the address, we'll see that this address has already been seeded with a little bit of Bitcoin, which I had done beforehand. Right now, I just have an address, but no way to actually talk to the live Bitcoin network. So I'm going to need to connect through one of BitPay's hosted Bitcoin nodes. First, let me just stash this as a variable so I can use it later. And then I'm going to instantiate a new instance of BitPay's Insight API. So I'll do var insight equals new explo.insight. And this is what I mean by Bitcoin can kind of feel enterprisey to work with sometimes. Like I actually had to instantiate something called an Insight API. I'm pretty sure IBM is legally obligated to send me a LinkedIn message when I'm done with this, but anyway. If I wanted to now query the live Bitcoin network for information about that address, I could do insight.address and then pass in the address, and now this will be a callback error result. And this is why I have that shell object, so I can just say shell.adder equals result and save the callback, and I could just query it through shell.adder. And I'll see that there's information about that Bitcoin address, including the balance in Satoshis. If I wanted to then, quickly do something like shell.adder.balance and see how much this is in US dollars, I could divide it by 10 to the 8th, and then multiply that by the price of Bitcoin, which is currently like $11,000 per Bitcoin, and I'll see that that's around $178 that's currently in that account. So something important to know about how Bitcoin works is what I mean when I say that the balance of this account is 1.6 million Satoshis. Now, Bitcoin accounts don't have balances the way you would think of a normal bank account as having a balance. What it actually has is control over a series of unspent transaction outputs, or UTXOs. So if I go to the Blockchain Explorer, I'll see that for this account, there were 2 transactions associated with it. Each transaction has inputs and outputs, but the outputs are what specify this account, and that's what gives us control over spending that money. So if I wanted to send Bitcoin to someone from this account, I wouldn't just send it out of this balance. What I would actually do is forward this unspent transaction output and use that as the input into a new transaction, and then that changes the UTXO from spent to unspent. UTXO is a binary state. The transaction output is either spent or it's unspent. It cannot be partially spent. If I wanted to send partial, some small amount of Bitcoin from this UTXO to someone, I could specify a small amount to send them, but then use myself as another output. But this entire UTXO would be the input, and then there would just be 2 outputs. One is myself, and I would generate a new UTXO. And I can query this from the command line as well. So if I did insight.get unspent UTXOs, passed in the address, error results, and then I will save the result on shell.utxos. And then if I did shell.utxos, I would see that there are 2 unspent transaction outputs associated with this address. And if I want to get the balance, per se, of the account, I would just look at summing the Satoshis that the account controlled. So you could do something like shell.utxos.reduce memo, I, and then just return memo plus I.satoshis, 0. And that would give you that account balance. One other thing to note also is that the unspent transaction outputs have this kind of unique identifier in it, this long thing, :0. Well, this is a way to uniquely identify any UTXO on the Bitcoin network. This hash right here is the hash of the transaction that the UTXO is associated with. So if I copied this into BlockCypher and just pasted the transaction ID, we'll see that this is the unique transaction and it had one output. And that is that UTXO. So 0 would be the index in the outputs of the UTXO, because you could have a lot of UTXOs associated with each transaction, but you can always uniquely identify a UTXO by specifying the transaction and then the index of that UTXO. So this little 2-tuple here is a unique reference to any UTXO. So now I'm going to send this Bitcoin to a different address. And I have a variable adder2 that I have a new address that I generated. And if we go to our blockchain explorer, we could see that this address has never been used. There's no transactions associated with it. First, I'm going to generate a new TX object, bitcore.transaction. And this TX object will just slowly build up over time by adding more and more data to it until it's in the right format. So first we need to decide which UTXOs we want to use as inputs into the transaction. I'm actually going to use both of them. So I could do tx.from, and then I think we had it on shell.utxo0 would be the first UTXO. And that will add data to the transaction. And we could actually look at the transaction as we're building it up by doing tx.toObject. And that'll give us like a nice JavaScript object that we could look at. So we'll see that this TX ID and then the output index is the unique identifier for that UTXO. And we have one UTXO associated with it, but we obviously can add multiple UTXOs as inputs, or else Bitcoin, wouldn't work very well. So let's do tx.from shell.utxos1 to add the second UTXO. And we'll look at the object, and we'll see that now there are two UTXOs being referenced as input. Next, I need to define the transaction outputs. Okay, a couple things to note here. First, every transaction requires that you specify a fee for the miners in order for the transaction to get mined into the blockchain. But you don't actually explicitly specify the mining fee anywhere in the protocol. The fee for the miners is always implied as the difference between the sum of all Satoshis from the UTXO inputs and the sum of all Satoshis from the UTXO outputs. So you need to do a little bit of math to make sure that you're leaving enough of a mining fee for your transaction to get mined. If your fee is too low, your TX might not ever get mined. If it's too high, you might be wasting money. This is a serious process because if you do your math wrong and apply a large amount as a mining fee by mistake, the miners will still scoop it up and you'll never get your Bitcoin back. In practice, this actually happens all the time. Hashtag welcome to crypto. I'm going to use a mining fee of 50,000 Satoshis, which is something like $5, and yeah, Bitcoin's not exactly cheap to send right now. Well, at least not cheap compared to something like Venmo, but compared to the cost to do a wire transfer from a bank or the cost of shipping gold, it still is pretty cheap. The Bitcore library lets you explicitly declare your fee so that it can do some sort of sanity checks for you to make sure that your numbers add up before you send your transaction. So I'll do tx.fee 50,000. And now if I look at my tx.toObject, I'll see that it does have this fee field here. But I still need to do my math to specify the outputs. So I'll do tx.to, and 2 will be adder2. And adder2, the amount that I will send to it will be shell.adder.balance, which is the total balance in that account, minus 50,000. And now if I look at my transaction, I'll see that it does have this output of that many Satoshis and this much specified for a fee. So right here, I'm sending all of my Bitcoin to this new address, less the miner fee. But if I only wanted to send a partial amount, I could define another output that had the exact same address as myself as another output. There's a handy function to do this in the Bitcore library called tx.change, where I could just do tx.changeAdder, and then that would look at the difference between what I have in the outputs and the fee, and just make a new output, sending that back to me. But just another thing to note, it's considered good practice in the Bitcoin community to never reuse an address twice, meaning that if I wanted to only send a partial amount, I could create yet a new address and then send the change there. So really I would need to make a new address like adder3, and then send the change to adder3, and then that would be the new account I used if I wanted to make another transaction. The reason you do this is to help preserve anonymity on the network by not having accounts with massive amounts of transactions that are maybe easier for people to chase or trace. Yet another thing to note. Notice that this output here doesn't just send Satoshis to an address. It actually has a script field, and we can dive into that by looking at tx.toObject.outputs. Or the first item, .script. And then we can turn this into human readable format by doing bitcore.script. And we'll see that it has this kind of opcodes, very similar to what you see on like the EVM for Ethereum. No, this is something called Bitcoin script.